Good afternoon, everyone, and welcome to this session of the Al-Khwarizmi Applied Mathematics webinar. It is my great pleasure to introduce today's speaker, Dr. Evrydiki Xenia Nestoridi from Stony Brook University. Dr. Nestoridi is an associate professor in the Department of Mathematics at Stony Brook. Her work is supported by the Simons Foundation and the National Science Foundation. Before joining Stony Brook, she was a research associate at the Statistical Laboratory of the University of Cambridge, a college research associate at the Emmanuel College, and an instructor of mathematics at Princeton University. She completed her PhD in mathematics at Stanford University under the supervision of Percy Diaconis, and she holds a bachelor degree in mathematics from the University of Athens in Greece. Her research lies at the intersection of Markov chains, combinatorics, representation theory, and probability, areas that beautifully connect theory and applications. We are very happy and honored to have her with us today. And please join me in giving a warm welcome to Dr. Evrydiki Nestoridi. And please, you can start.
Thank you so much for the introduction, and thank you for inviting me. I was particularly happy to receive and accept this invitation because the email said specifically that if I could, I should talk about limit profiles, which is one of my favorite subjects. So I hope to be able to, convey what this object is about and few of the open questions. And I do welcome conversations, so feel free to either unmute yourself and ask questions or ask something on the chat. Now, I might not be able to see the chat very easily, so please let me know if there's a question. Okay, to define everything, I like to introduce one card shuffle that I really think will help us navigate the talk. In card shuffling, we start with a deck of n cards, distinct. And let's say today we're going to shuffle according to random transpositions, at least at first. Let me change this. Okay, when shuffling a deck of cards according to random transpositions, what happens is that the left hand touches a card uniformly at random. The right hand touches a card uniformly at random. It might be the same card. It happens with some tiny probability. And then the two cards you have, you swap. If it's the same card, you stay fixed. So pick two cards uniformly at random, independently, and then swap them. That's the random transposition card shuffle. The question we like to ask, or one of the questions.
Sorry,
yes?
by swapping, you mean that they change the place?
Yes, exactly. Okay. So if you pick card I, which is in position I at first, and card J, which is in position J, swapping means that card J goes to position I, card I goes to position J, but everything else remains fixed.
Okay.
Yes. So the question is, swap can also mean transpose, in case I use that word also. The question is, how many repeats, how many times do we need to perform this process until we are shuffled well? And I will define everything mathematically very soon. I just want to roughly show you in English what a question in mixing times is. Like how many repeats until shuffled well.
Sorry, another question, because I'm not good in English. Shuffled well, you mean that every card changes of place?
Okay? No, it means that you need to be close to the uniform distribution. Any card is equally likely to be at any position, this type of statement, but I will make it mathematical very soon. Okay, so hopefully the English might be so-so. Hopefully the math will be accurate.
Thank
Okay,
you.
give me a moment. Yeah. So again, with hand waving type of terminology, I will say that a theorem that I will precisely write by the end of this talk is due to Diaconis and Sasha who proved that it takes 1/2 n log n steps to shuffle well. And again, I will precisely write the theorem. So if you have n cards and you perform this specific randomized algorithm, you need 1/2 n log n steps to shuffle well. And you will notice that this is forever. This is very, very long. So of course, this isn't the way that we actually recommend that people shuffle a deck of cards. So why would we care about this card shuffle? Well, two reasons. One, there could be more, but two reasons are: one, this is the best approximation model to how genes behave in DNA sequences. So biologists care about this type of card shuffles. We actually know the exact model that the genes follow, but it is not as well understood as this one. So this is used as an approximation for sharper answers. And then a mathematical reason is that Diaconis and Shashahani actually introduced a technique that can be applied in random walks on groups, where they use the representation theory of the symmetric group to produce an answer like this. And we will see a little bit of that too. So this is roughly the model that we can keep as a pilot in our mind today for the rest of the talk. But now I'm ready to give the math context. And so in card shuffling, the first thing to notice is that if you have a configuration of a deck, if you look at the set of configurations, that corresponds to the symmetric group on n cards. Why is that? Well, when we buy the deck of cards at the store, all cards come in order. So let's say we have them in order 1, 2, 3, all the way to n. That corresponds to the identity element of the symmetric group. Say we were to swap the top two cards. That would mean that card number 2 comes to the top, card 1 moves down, and so on. That corresponds to the transposition 1, 2, and so on. Every configuration of the deck gives us a permutation and vice versa. So the configuration space of this Markov chain, of this card shuffle, is the symmetric group. And this is why we will consider two permutations, two elements of the symmetric group. And we're going to build up the transition matrix as follows. The XY entry of this transition matrix P will give the probability of moving from X to Y after one step. So you can see that this transition matrix heavily relies on the model that we start with. If one changes the model, the transition matrix will change too. In particular, if we really want to write the formula here. So this entry is 1 over n if sigma is the identity, because with probability 1 over n, you pick a card at random. With probability 1 over n squared, you have touched the same card, but then you add all possible cards that you could have touched with the left hand, and this is why this turns into an 1 over n. Then another possibility is that you choose two different cards and you actually swap them. So if you perform a transposition AB, this means that card A gets swapped with card B. Then this type of move happens with probability 2 over n squared, and anything else happens with probability 0 in one step. So I'm just trying to make a point that this is an n factorial by n factorial matrix that has a lot of zeros at first. And we will care to study powers of this matrix. So we are going to raise this matrix to the power of t. And now if we want to study what the xy entry gives, this will give the probability of moving from x to y again, but now after t steps. You somehow need to convince yourselves that this is how matrix multiplication works. It's like a convolution type of argument. So the question now is, how do we study these large powers? And why do we want to study? Before I say that, what happens is that under certain conditions that I will throw under the rug, these conditions are met by our model here. Under standard conditions, if we send t to infinity, this will look more and more like 1 over n factorial, which is the uniform measure on Sn. Sn has n factorial elements. So this matrix, the higher the power you raise it to, will look more and more like a matrix whose every single entry is 1 over n factorial. And the first subject of this talk is to understand this convergence, which means that we need to understand high powers of a matrix. And if we are going, if we go back to the linear algebra classes we took in undergrad, this means that we could potentially talk about eigenvalues and diagonalizing this matrix.
Sorry, just a small question. Why 2 over n squared? Can you explain again the probability 2 over n squared?
Yes. Although it won't matter to us so much at the end of the day, because left hand can touch card A, for example, right hand can touch card B and swap. That happens with probability 1 over n squared. But it could also happen that the left hand touches card B and the right hand touches card A and they swap. So this move can happen with two ways. Either the first hand touches card A or it touches card B, and then the other one touches the other card.
Okay.
That's why it is doubled. Yes. Okay. So the goal now is to study this convergence. And the usual norm that we use in mixing is the total variation distance. One can use the L2 norm, and in fact, this will appear later as well. But this is the most popular distance. So in particular, just to make it clear that this distance is a distance of probability measures, we will start writing this like this. So we will put the starting point down here, because then as y varies, this is a probability measure. In fact, so the x row of P is a probability measure because somehow you need to land somewhere with probability 1. And in the setup for today, you can take X to be the identity. When you're doing a random walk on a group, it doesn't matter so much what your starting point is. So just for this talk, we will be looking at the total variation distance between the identity row of P to the T minus the uniform measure. So this is now notation. This is total variation distance. So TV stands for total variation distance. This is the uniform measure. So this is defined to be 1/2 of the L1 norm between these two, say, identity here. And then here we add over all y's in Sn. Let me write this a little bit better. Okay, so we look at all differences between the y entry of the identity row of p to the t and the uniform measure. We take the absolute value and we add all these errors. This 1/2 is just so that this function takes the values between 0 and 1, and one can, have some sort of probability behavior there. So this is the measure, the distance that we consider between probability measures. And usually in Markov chain mixing, we consider all possible starting points, and we take the maximum of the total variation distance with respect to the starting point. We will not have to do it for this talk. The mixing time question. So that type of question that we asked, how many repeats do we need to perform to be shuffled well? That means that you give me an epsilon, you tell me what the error, what the distance between the two measures is allowed to be. And I should be able to tell you what is the first time such that this quantity becomes less than epsilon. And just to abbreviate, well, let's call this dt for today, for now, so that I don't have to copy it all the time. So that's what the question translates to. I need to know how many steps to take so that the total variation distance becomes less than epsilon. And with that being said, I can now write the theorem of Diaconi-Senshashahani so that you see what a theorem in mixing times looks like precisely and not just in English. So they said that for random transpositions, if one takes 1/2 n log n steps plus a little bit more, so of order n, something of smaller order, we will see what c is in a second, then the total variation distance is less than e to the minus c, where c is something positive. Now, I might be lying here. This e to the minus c, it might be e to the minus 2c or something like that. I will be more careful with what I write in a little bit. For now, it's something that we explicitly know. Is there a question? Okay.
No question. No.
No question. So this means that in particular, if we take c to be log of 1 over epsilon, then dt becomes less than epsilon, just to connect it with the epsilon type of definition. A second thing is they also noted that if you take a few less steps, then if we take total variation distance at this time t and we send n to infinity and then c to infinity, then you get 1. You get the maximum value of the total variation distance. You can imagine this as somehow at this time dt is bigger than 1 minus something small. They have a precise inequality. I don't bother to remember this because this isn't the important part of the talk. What is the important part of the talk is first of all, this notion of cutoff. So what their theorem describes here is the following picture, that if you plot the total variation distance with respect to time, what this part 1 and part 2 say is that, well, when you start at the identity, the total variation distance is 1, and it remains equal to 1, and then suddenly there is a very sudden drop happening at 1/2 n log n, And the window of this decay is of order n. Now, this is always confusing me rather than helping me, to be honest with you, because here they should really be having a limit as n goes to infinity. But this is the picture that you see when cutoff is trying to be explained. Let's define cutoff because, as I said, I want to talk about limit profiles and I want to give you the definition of what we have. So, motivated by the random transpositions, the definition of cutoff is the following. So for today, I restrict myself to the symmetric group, but you can imagine that you can have another group, a graph, you can have all sorts of stuff and define your Markov chain and run your algorithm. As long as you have a space, a sequence of Markov chains on a sequence of spaces, then everything works well. So here, the sequence is Sn, is inside Sn plus 1. And, you can perform random transpositions on Sn, and these moves are contained inside Sn plus 1 and so on. So we say that a sequence of card shuffles or a sequence of Markov chains on Sn, and in fact, let's even define the sequence to be xt. And we have it running on n, is said to exhibits cutoff at Tn with window Wn if 1. This window is of smaller order than the main term. This was the comment that this is of smaller order. So n is the window, Wn. 2. If we take the total variation distance at time Tn plus Cwn, and we send n to infinity, and then c to infinity, this will give you 0. So let's go back to the theorem and see. That is this leg of the theorem that says send n to infinity, nothing changes, but then send c to infinity as well, then this goes to 0, then the limit will be 0. And the third part, I already wrote it precisely in that form in the theorem as well, which says, again, take n and then c to infinity, but do minus steps, take a few less steps. Then your total variation distance is 1. That's what cutoff is about. And it is fully motivated by random transpositions and this picture over here. Now, the community has spent a lot of energy in developing an if and only if criterion. When does this criterion occur? And the main progress has been done by Justin Salles, who has an entropic criterion for cutoff. But then whenever these type of criteria don't apply, then we have specific examples that are famous Markov chains that people care about. And one thing that is also important is that when you study a specific example, you want to know exactly when cutoff occurs, while so far the criteria we have don't tell us when cutoff occurs, just whether it occurs or not. But these are the two directions so far in the field. A third direction that has started since 2018 mainly is the limit profile. So now we can finally discuss the limit profile, which comes as part 4 sort of here of our definition. I mean, the cutoff definition is done, but it is a definition that I want to give, which says, what if we throw away the limit as c goes to infinity? So if this function of c exists, sorry, exists for C, either positive or negative. I'll write in R. In the case of continuous time Markov chains, it makes sense to say that C is in R. Then this thing is called the limit profile. And this is an iffy type of definition for many reasons. First of all, what this definition is trying to capture is, I don't want just the limits, because cutoff only cares about this 0, 1 behavior. We care about the exact formula of this function. What is the decay like? Can we say precisely? The iffy part is that this requires knowing an optimal type of window. Does this limit exist, and so on. So, and also in my definition here, I sort of require cutoff to define it, but there are examples where we have limit profiles and cutoff doesn't occur. So I'm just doing my best to give a definition and tell you all I know about this object. So first of all, let's start with something I do not know. I do not know when a criterion saying that if the Markov chain of the card shuffle satisfies A, B, C, then this limit exists. I do not know that. I'm going around the world asking people to think about it. I would be so happy to hear of any progress. So what do I know about this? First of all, for specific card shuffles, for example, Bayer Diaconis, the riffle shuffle. I want to mention riffle shuffle because this is the way that people should be shuffling a deck of cards. It's the shuffle where you roughly cut your deck in half and then you riffle. That's their famous theorem that, if you do this 7 times, then you can shuffle a deck of 52 cards. Then they know the limit profile is given in terms of a Gaussian. So this goes 40 years ago, we already could see some limit profiles. It's just that people didn't know how to study them. So every now and then people could get their hands on this specific function. Another instance where this happened is in the work of Lubetsky and Perez for Ramanujan graphs. So random walks on Ramanujan graphs. There again, they had some central limit theorem type of behavior, and they got the limit profile. If you don't know what I'm talking about, no worries. I will come back to it. All I'm trying to say is that there are there are regimes where we know the limit profiles, and it's usually some sort of statistic. So again, some sort of biased exclusion process. That's why I wrote ASEP on a closed segment. This is a more recent, this is work due to Bufetov and Nejar. We also know the limit profile. All these cases, there was a specific statistic of the walk that gave away the limiting behavior. Here, they looked at the number of increasing subsequences of the permutation. Here, they studied the non-backtracking random walk on the Ramanujan graph, and then they said, okay, how many times do we backtrack? So there was a central limit. There was a speed argument and a central limit theory. And here it's the bias that you are always very close to one end of your segment. None of these papers introduce some sort of technique. And this is why I say that for me, the subject started in 2018 when Teissier refined the arguments of Diaconis and Shashahani and used Fourier inversion to actually introduce the first technique for how on earth do we find this limit profile. So his exact result was that for random transpositions, at time 1/2 n log n plus c. The limit profile is equal to the total variation distance. I will write it dTV now. It's again total variation distance between a Poisson 1 random variable and a Poisson 1 plus e to the minus c. Which is, it is actually a very pretty formula. I mean, we write it like this just to make it concise. This was long conjectured by Matthews and Percy Diaconis because the statistic behind it is the number of fixed points. So if you take a uniform random permutation on the symmetric group, the number of fixed points follows a Poisson 1. That's a classic fact. And as you take n to infinity, so if you perform random transpositions and take n to infinity, the number of fixed points will behave as a Poisson 1 plus e to the minus c. Now, the fact that only fixed points matter is not so clear in Teyssier's work. He has to take care of bigger cycles as well. But the fact that that's what happens at the end of the day, this was more explicitly proven later by Vises Jain and Mehtab Soni. So just a beautiful paper if anyone wants to read something for fun. Both of these papers are beautiful. Okay. However, back to the technique of Teyssier. I'll come back. Yes, I'm ready to come back to the technique of Teyssier. So, any questions, first of all, on at least the theorems of Diaconis and Shashahani and Teyssier, what we're talking about? It's a good moment to stop and see if we understand each other. Okay? No questions, I guess. So how do we prove something like Diaconis and Shashahani, and what are the tools, and what are the tools for something like Teyssier? So basically we pass to the L2 distance via the spectrum of the transition matrix. How do we do that? So random transpositions, let's say that P is the transition matrix of random transpositions. The important thing about it is that P is symmetric. That has to do with the fact that if you perform a transposition, the next step, you might perform the same transposition, and these two moves are equally likely to happen. So if you do a move, you might undo it on your next step with equal probability. That's what it means to be symmetric. Okay, then spectral theorem. The spectral theorem says that P has real eigenvalues and an orthonormal eigenbases. So I'm going to throw the eigenvectors under the rug for this talk. They do play a role in general Markov chain theory, but I prefer to keep this talk as simple as possible. In terms of the eigenvalues, let's call them beta I. I runs from 1 to n factorial. Remember, this is an n factorial by n factorial matrix. Lots of eigenvalues. So what do we know about these eigenvalues? We know that the first one is always equal to 1. The next one will be strictly less than 1. Then you might have repetitions all the way to the n factorial one, which is strictly bigger than -1. These are standard graph theory type of statements. And the fact that here we are not allowing equality, it has to do with the fact that random transpositions generate the symmetric group, and the identity is allowed. So staying fixed is allowed. This is why you don't see equality here and there. Okay, so to prove cutoff, this is an oversimplification of what Daikon-Shahani did, but accurate. What you do is that you do Cauchy-Schwarz. I think I always put an extra something here. And what Cauchy-Schwarz says is that if you raise L1 norm to the power of 2, then you can bound it by the L2 norm, which in this type of setup, when P is symmetric, is equal to the sum of the eigenvalues to the 2T, but you start adding from the second one. So you remove this guy. Okay, why is this helpful? Well, first of all, notice that all these numbers in absolute value are less than 1. And so if one sends t to infinity, this indeed goes to 0. So we retrieve that convergence that I stated at the beginning of the talk. The whole question now is to actually see how t depends on n. What is the optimal t we can take so that if n goes to infinity, this whole sum goes to 0. In other words, the first task is to find these eigenvalues. And again, this is an n factorial by n factorial matrix. It sounds tough, but this is where Daikon-Shahani used representation theory and Fourier transform arguments. So this is how you find the eigenvalues when you have a conjugacy invariant random walk. And then once you have them, you actually need to get your hands dirty and figure out how this sum behaves. Okay, so that is for cutoff. But for limit profile, what Tessier had to do, and again, it's an oversimplification, is I said Fourier inversion. So doing Fourier inversion, and this is actually where, for once in my talk, I will use the orthonormal basis for a moment. I shouldn't have thrown it under the rug, it seems. Just to write down this formula, that the total variation distance, again, we start at the identity. I want to put it down there so that it's clear, is actually equal to this formula. Let me write it correctly. I think the absolute value is over here, but you know, if I'm doing it wrong, it doesn't matter for the talk. We won't play with this formula much. What I want, and here, what is X? It's the identity. Okay. So there is this explicit formula. And in Tessier's case, in terms of these guys, you see characters of the symmetric group appearing. And we also know the eigenvalues due to Daikon-Shahani. So he really got his hands into the representation theory of the symmetric group to be able to say that, look, only the first few terms matter in the limiting behavior and everything else goes to 0. That was his argument. Again, it was very, very difficult to prove, but in fact, in a paper with Sam Olesker-Taylor later, we used this technique for more conjugacy invariant random walks, and we actually generalized his technique to work for general Markov chains. Where we said that, look, if you care about the limit profile, what you can do is exactly what I said already, is to consider only a subset of your eigenvalues, consider only those terms. So here, instead of I summing over all, we will only consider these specific terms that we care for. Okay, I will write it for the symmetric group but again, as I said, it's for general Markov chains. So we take the difference between the whole sum and just a few terms. We do triangle inequality and get some error term of this form, something like that. Okay, so all I'm saying is that suddenly we have two techniques, one due to Tessier that works very well for conjugacy invariant random walks, and then one for general Markov chains. And then, okay, so suddenly, we have some tools to study this limit profile object. I do want to go into a third technique, which allows us, well, let's talk. It's called comparison of limit profiles. And the best way to explain it is through another card shuffle that is called star transpositions. So remember, in random transpositions, you touch two cards and you swap them. In star transpositions, you choose only one card uniformly at random. And then we swap it with the top card of the deck. And that corresponds to performing star transpositions, meaning transpositions of the form 1A, where A could be any of the cards. So that's also a generating set of the symmetric group. And the idea is that roughly performing two star transpositions, it's very close to performing random transpositions. Not exactly the same, but very close. And that depicts in two ways. One is in terms of cutoff. So Diaconis proved that star transpositions exhibits cutoff at n log n with window n. And it is not a coincidence that this shuffle takes twice as long to shuffle than random transpositions. It is this heuristic that I told you behind. To prove it, it's a different type of story. Diaconis's proof relied on the work by Flato, Odlyzko, and Wales, who diagonalized the transition matrix of star transpositions. Why am I bringing up this shuffle? Well, firstly, the theorem from a few years ago says that star transpositions and random transpositions have the same limit profile. In particular, for star transpositions, if we take n log n steps, we get that the limit profile is exactly the same, meaning the total variation distance between two Poissons, and so Poisson 1 and Poisson 1 plus e to the minus c. It would have been whatever random transpositions had. So it's hard to go and do Tessier's work for this card shuffle. It really only works for conjugacy invariant random walks. So what is the idea behind proving this? It's this comparison technique. And I really want you to think of random transposition and star transpositions as I'm writing it down, which says that assume that you have a transition matrix P of a card shuffle. Okay, let P of a card shuffle, of a symmetric card shuffle. meaning that P is symmetric, that exhibits cutoff at Tn with window Wn and eigenvalues beta I. Okay, so that's random transpositions. Now star transpositions. Let Q be another transition matrix. Again, symmetric with cutoff at Tn bar and window Wn bar and eigenvalues, not beta again, let's say Qi. Then the limit profiles, let's say for P, and here it is C, and the limit profile of Q at C. Here, this really is implied at time Tn plus Cwn, and here at time Tn bar plus Cwn bar. Again, we will do a Cauchy-Schwarz, is less or equal than the sum. We take the eigenvalue of beta I to the cutoff time of the corresponding Markov chain, minus Qi, the corresponding cutoff time, squared. And then we send n to infinity. Now, there is a very important thing that I have forgotten to write. So I say we have two Kirchhoffs with this type of spectrum. There needs to be a connection between the two Kirchhoffs, and the connection is that these matrices commute such that P times Q is equal to Q times P. This is big. We cannot forget that. Then that. Okay. Even though this might feel very restrictive, random transpositions commutes with any random walk on the symmetric group because it's a conjugacy invariant type of set. So it's not too much to ask, is what I'm trying to say. In particular, star and random transpositions commute. And then the question is, how do their spectrum behave at the corresponding cutoff times? And really, in the analysis, what happens is that beta I squared is roughly equal to Qi. Now, again, one more moment at this comparison test. One thing that is different from what I said is that now these guys are not ordered from smaller to bigger as I had it over here. Here. No, the way that we pair them is that this commutativity property that we demand means that P and Q are simultaneously diagonalizable. So beta I and Qi share the same eigenvector is the way that we pair them here. Okay, so we take one eigenvalue of P, we raise it to the cutoff time plus C times the window. We take the corresponding eigenvalue and raise it to the corresponding cutoff time. We subtract them and then raise them to the power of 2 and then add all these errors. And so the whole point now is that for star transpositions and random transpositions, this limit is 0. This is 0, which makes the left-hand sides equal. And this is how we prove that whatever limit profile random transposition has, the same limit profile the other will have as well. Now, I want to finish with the final thing that I know about limit profiles, and then I have told you everything I know, which is, okay, I cannot tell you when this function exists. I told you that I still don't know, but I can tell you that if it exists, I have a criterion for telling you when it's continuous, for example. I care about the properties of this function. And I will end with this type of theorem, the continuity theorem. That says that, again, let P be a card shuffle on Sn, symmetric with cutoff, and assume that the limit profile when starting at the identity exists. So it is a function of C. I'll put a dot there. If I'm sticking with discrete time Markov chains, so in this case, for the lemma theorem to work, all beta I are positive, are required to be positive. But if you go to continuous time Markov chains, you don't need that. And the following quantity is bounded. So this is the window of the cutoff time. And this is something that looks like the L2 norm. In fact, let me get rid of the eigenvectors. I want to give you the simplest version of this lemma, which works for random walks on the symmetry group. If this is bounded, say by a continuous function on G, where G is continuous, if you can find a continuous function or a bounded function to bound this quantity, then the limit profile phi is continuous. Okay, I want to repeat this once more and then I'll end. So I'm just saying that the final thing that I can prove about limit profiles is that if you are in the symmetric case and you do have cutoff of Tn with window Wn, and you assume that the limit profile exists, this is a big if, I cannot prove existence, then checking this type of quantity, which is something like an L2 quantity, and being able to bound its limit by something continuous or bounded, will give us that f is continuous. I want to make it clear that this quantity is computable. Like for many Markov chains, we know the eigenvalues, the cutoff time, it's something that you can do by hand. And I do have a list on my paper of something like 7 examples where we can compute this thing. So it is checkable. And in particular, I do have examples of Markov chains where I cannot tell you what their limit profile is, but if it exists, I can tell you that it is continuous. And I want to write this down, one of them at least, is the random to random. So I'll tell you what random to random does, but before telling you, I want to say that for random to random, we do not know if the limit profile exists. In particular, we don't know what it is, but if it exists, then it is continuous. If it does exist, then it is continuous. And just for the record, random to random, what it does is that you have a deck of cards, you pick a card uniformly at random, you remove it from the deck, and then you remove it back to a uniformly at random position. That's what it does. Okay, I will stop here. Thank you for your attention.
Thank you, Ivita, for this nice talk. Are there some questions, please? What do you mean here by Q is continuous?
It's not Q, phi. This is the limit profile.
Yes, sorry.
Is a continuous function of C. For example, if we go to this theorem of Teissier saying that the limit profile of random transposition is given by this, one can easily check that this is a continuous function of C.
Okay.
And that is, it's also confirmed by my theorem. It's not only for random transpositions. I'm saying that if some conditions are met, you expect to see a continuous function as the answer.
Okay.
I must say that Teissier has a beautiful paper saying that any decreasing function from 1 to 0 can be attained as a limit profiles. In particular, you might see some sort of step function.
Okay.
So there are discontinuous functions that can be achieved as limit profiles. And my final theorem just says when that's not the case, that you will be seeing continuous stuff if an L2 condition is met.
Okay. Does your approach apply only to reversible chains, or do you think that it could be extended to non-reversible Markov chains in the future?
So far, when we use the spectrum for upper bounds or limit profiles, we need reversibility because it is important to have an orthonormal basis, basically.
Okay.
We haven't been able to get past that.
And what motivated you to study the limit profiles rather than focusing only on mixing times?
The beautiful paper of Teissier. Like when I read this paper, I just thought this is beautiful, that we can say much more than just the limit
Okay.
to infinity. And in fact, this is what, if someone needs to program, that's what they should care for. They should care about the exact behavior rather than what the answer at infinity is.
Mm-hmm.
Yeah.
Okay. And for the last slide, your function G, you need a continuous function or just a bounded function? A bounded function suffices, or G must be continuous?
Bounded is fine. Bounded is fine, but because C is in R, continuity also is okay, because continuous in R doesn't mean bounded.
Yes.
So that's why I'm like, continuous or bounded, you're good.
But continuous is not necessarily bounded, no?
I agree. And bounded isn't necessarily continuous either. So I'm saying if you get one of the two, you're good.
Okay. Mm-hmm. Okay. Are there some other questions? Your problem here, it is not similar. Are there some first earners behind this problem, your problem here?
I mean, so you said earn first earns, right?
Yes.
So if you look at this work with Sam Olesker-Taylor,
Okay.
this one, we do get limit profiles for some earn first earns using this technique.
Okay, so you applied your results for such
We apply the
earners.
techniques, we apply our techniques to get some limit profiles of earn models. Yes.
Okay.
So it's the only work I know applying this type of technique. Then very recently there was a paper for the limit profile of the Bernoulli Laplace earn model. So I sent you a paper. Search who cites us, and you'll see Dominic Schmidt and Samuel Lesker-Taylor. So Lesker-Taylor and Dominic Schmidt did the Bernoulli Laplace earn model. And these are the only earn models that I know that we know the limit profile of.
Another question, maybe the last. In your talk, I think that the limit profiles involve Gaussian or Poisson type approximation.
Yes.
Okay.
So in the talk, indeed, but I didn't, there are examples, where are they?
Okay.
Like this asymmetric exclusion process where you see a GUE, for example. Here you see a GUE. And then again, I told you that Lucate-Hessier proves that any decreasing function from 1 to 0 can be achieved as a limit profile. So don't be fooled a little bit by the specific examples I have given you.
Okay. Okay. Some other questions, please.
These are all great questions you asked, by the way. So.
Okay, if not, we have to thank again Dr. Ivita for this nice talk,
Thank you
and
so much.
and see you after 2 weeks.